guys, this video is on our last method in solving systems of equations called the elimination method. What we want for the equations in the elimination method is for the like variables in each equation to line up vertically. For example, in number 1, as you could see, the terms with the x in it are lined up vertically, with the y lined up vertically, the equal signs are lined up, and the numbers with no variables in it are lined up to the right side. It doesn't necessarily have to be in this order, which both of these equations are in standard form. It would help if they're both in standard form, but just as long as the like terms are lined up vertically, that would be fine for the elimination method. Once we know that the terms are lined up, we're going to look to either add or subtract these equations vertically in order to eliminate one of the variables. For example, I know addition in this case will eliminate the y terms because negative 3y plus 3y is 0. When I add the other like terms vertically, 4x plus 2y is 6x, and negative 22 plus 16 is going to give us negative 6. When we now divide the 6, what this does is allow us to solve for the x variable. Now we know that a solution to a system is an ordered pair. Now that I have the x value of the ordered pair, we now have to find the y value by substituting that x into one of the original equations. I'm going to substitute into our first equation 2x plus 3y equals 16. I know that x is negative 1, so we have 2 times negative 1 plus 3y equals 16. When we simplify, we'll get negative 2 plus 3y equals 16. I'll add the 2 over to both sides, and when you divide the 3, we get that the y is equal to 6. We're not going to leave our answer as just two values. The solution is an ordered pair. I know that this would represent one solution, and that would be the ordered pair negative 1, 6. If we were to graph this system, we would see that these two equations would intersect each other on the coordinate plane as lines and at the ordered pair negative 1, 6. I'm going to skip to problem number 4. As you can see, the like terms do not line up in these two equations. So what we want to do, I think the easiest way is to put them in both slope-intercept form. Since the second equation, all we'd have to do is add the 6x to both sides, in which we'd get the equations 3x plus y equals 3. That's still the first one. And if I add the 6x over in the second equation, we would get 6x plus 2y equals 6. Now our like terms are lined up vertically, so I can begin the elimination method. The next thing you're going to want to do is decide whether you want to add or subtract the two equations in order to eliminate a variable. In this case, neither of them would work, adding or subtracting, because the coefficients for both of the terms with the variables in it aren't either the same or opposite signs. So what you want to do is make one of the equations having the same coefficient as the other equation for one of the variables. A quick way to do that is to find a number that we can multiply one equation by so that we could have the same coefficient. For example, I can multiply the first equation by 2 to then get our equation 6x plus 2y equals 6. I'm going to rewrite our second equation, which happens to be the same thing, but now I know if I subtract, I will eliminate not only one of the variables, but actually both of the variables in this case. 6x minus 6x is 0, 2y minus 2y is 0, and 6 minus 6 also happens to be 0. Since in this case our variables eliminated, and we got the expression 0 equals 0, which is true, I know that this would represent many solutions, and that if I were to graph both of those equations on the coordinate plane, it would show that they would be the same line on top of each other with many ordered pairs in common. I'm going to now skip to number 5. As you can see, both of those equations, the like terms do line up. It's okay that they're both in slope-intercept form. As long as the like terms and the equal signs line up with each other, then we could start adding or subtracting to eliminate. In this case, we could immediately eliminate the variables by subtracting them from each other. Y minus y is 0. Negative 2x minus negative 2x is 0. And 2 minus negative 5 is 7. In this case, since both of the variables were eliminated, this is actually a short problem, and we got a false statement, 0 does not equal 7, I know that this would represent no solutions. If we were to graph those equations on our coordinate plane, we know they would be parallel since they also have the same slope. Those are in slope-intercept form, so we know the slope for both of them is negative 2. They have no ordered pairs in common, representing no solutions. What I'd like you guys to do is try number 2, 3, and 6 yourselves. Remember, for number 2 and number 6, you want the variables to first line up. And also, you're going to maybe have to multiply one or both of the equations in one or both of two of these problems, so that when you add or subtract, you would be able to eliminate a variable. Once you get your answers, play the video for an explanation of each. Here are your answers for 2, 3, and 6. Again, number 2, the variables don't line up, or the like terms don't line up. So what I did, and a good rule of thumb is you could always just put them both in standard form, so that now our variables line up. What operation would eliminate a variable? In that case, it would be addition would eliminate the y's, because y plus negative y is 0. We would be left with 5x equals 15 when adding the rest of the like terms, allowing us to find the x value equal to 3. I'm then going to plug that into one of the equations above. I plugged it into our first equation in our original system, getting the y value of 5, showing us that there is one solution, which is the ordered pair 3, 5. In number 3, the like terms did line up with each other. However, we couldn't immediately add or subtract in order to eliminate a variable. So what you had to do is look for a number you can multiply one or both of the equations by, so that the coefficient for one of the variables are either the same or opposite, so adding or subtracting would eliminate. If we multiply the first equation by 3, we would now end up with these two equations, in which adding would eliminate not only one variable, but both of the variables. And on the right side would also eliminate 12 plus negative 12, giving us the answer 0 equals 0. Since this is a true statement, we would get the answer of many solutions. If we were to graph this on our coordinate plane, it would be the same equation or the same line on top of itself, sharing many ordered pairs. And lastly, problem number 6. The like terms were not lined up. So what I did again is put it in slope-intercept form. Standard form. It's okay that the a value is negative. We're just rearranging the terms so that the like terms are lining up. If I were to add or subtract, neither of those operations would eliminate a variable. So what we had to do is think of a number to multiply one or both of the equations by. What I did was multiply the first equation by 2 and the second equation by 5. Notice that that gave the coefficients either the same coefficient or opposite coefficients for the variable. not only one of the variables, but both of the variables. So when I added, not only did the x eliminate, but so did the y, and we get the expression 0 equals 92. Since 0 does not equal 92, it's a false statement that would represent no solutions. If I were to graph these two equations, they would be parallel to each other on the coordinate plane, showing they have no ordered pairs in common and no solution, no ordered pair that's a solution to both of the equations. If you guys have any questions for this lesson, please let me know, and I'll talk to you soon.